In this example, we're going to talk about the energy stored in a spring using Hooke's law. Here I'm going to use the letter U to represent potential energy. And the K is indicating that it's from a spring because we usually use the letter K for spring constant. So you could put an S here and that would be just fine. But I'm going to call it K for the K in Hooke's law. So UK will be potential energy stored in a spring. We're going to set up the situation where we have a spring. That's my super awesome drawing of a spring attached to a 7 kilogram block. This spring is going to have a force constant of 200 newtons per meter. And we're going to define the equilibrium position of the spring, so when it's not stretched or compressed, just sitting at rest, just chilling, x equilibrium, to be at the origin. Now why do I do this? Because then I want to measure how far the block moves from its equilibrium, and that's the value I put here in the potential energy in a spring. In fact, I should call this delta x because it's the change from my equilibrium position. So every time I have to subtract off whatever my equilibrium position is, but if I just say, hey, let that be the origin, then I'm always just subtracting 0 from how far the block moves. And that seems much easier than, say, subtracting 4.837 or whatever. So this is our original situation when the block is at equilibrium. We're then going to take the block. I'm not sure what happened with my camera there, but it all went all white balancy. And we're going to push on that block until the spring is compressed. And the distance we're going to compress it from equilibrium, so if this was my equilibrium, is 11 centimeters. Now if you think about this up here, if I want to check how much energy is stored in the spring when it's not displaced at all, then my delta x is just 0, so there's no energy stored in the spring. Now here, if I check how much energy is stored in the spring, delta x squared is 1/2 200 newtons per meter times 0.11 meters squared. Notice I have to use meters because the force constant has meters in it. That is 1.21 joules. And this is going to be our starting place for the rest of the problem. So what that means is I have put some kind of work into this system. If you watch my video on the work kinetic energy theorem, I did work when I took this block and pushed it in. And that work is now stored as potential energy in the spring. I'm not going to apply any more forces from the outside of the system, so any forces happening next are going to be internal to the system. And that means that this is all the energy the system will ever have. So this is my total energy. And figuring out what your total energy is often the critical point in solving an energy problem. Because once I have this number, once I know that this is how much energy was put into the system, and that from now on the system's going to be left alone to do its own thing, this is all the energy it can have, unless someone comes along and pushes on it again. We're not going to let that happen in this problem. So this is our total energy. As long as there's not friction or any other, say, force that can take energy out of the system, then this will be our total energy the whole time. So what can we do with that? Well, if I want to ask you, for example, what's the speed at a whole bunch of different positions, so let's say I want to ask you what's the speed at 9 centimeters from equilibrium, what's the speed at 5.5 centimeters from equilibrium, and what's the speed once we get back to equilibrium. So I want to know when the block is at each of these points, what is its speed? Well, here's what I can do. Once the block has a speed that's not 0, that means it has a kinetic energy that's not 0. Well, we can't create or destroy energy, and no one's allowed to push on our system, and we're not including friction. So our total energy has to add to this. Well, it's still attached to a spring at each of these places. So that means that we are not sure, but our elastic or spring potential energy doesn't have to be 0. So it might be greater than 0. What can we do with that? Well, think about what a total means. My total energy in the system is going to be my elastic potential energy, or spring potential energy, plus my kinetic energy. Well, I already know what this is, my total energy. I found it. And I know the equation for these other two things. And like I said, I should be careful. It's delta x squared. So what I'm doing is I'm plugging in the distance from equilibrium at each point and solving for v. So why don't we just go ahead and solve for v, and then just plug in these numbers and pop out the answers. So if I do some algebra here, and you should check me on this, but if I do the algebra, I get that it's the square root of 1.21 joules minus 1/2 k delta x squared divided by mass times 2. And that last times 2 comes from here, the 1/2 in front of mb squared. And then I'm just going to go ahead and plug in all the numbers except for displacement from equilibrium. And the mass originally was 7 kilograms. Okay, well, how is that helpful? Well, now I could grab a calculator and do this once each for these 3 displacements. If you happen to have a computer with Excel, or even better yet, MATLAB or Python handy, then we can just have the computer do this using this as our equation. So my delta x will be my input, and I want the computer to give me my velocity. So this is kind of algorithmic thinking. I have some inputs and desired outputs, and a computer is really good at that kind of thing. If you're not so comfortable with computer programming at this point in your life, that's fine. Just grab a calculator and put in delta x is 9, get a v out, put it in 5.5, get a v out, put it in 0, get a v out. And honestly, for just doing it 3 times, this problem is simple enough that, and probably faster to just do by hand. But if I had to do this, say, 1,000 times, or 1,000,000 times, then I would want the computer to handle this for me. So let's try each of these. 9.0 centimeters, 5.5 centimeters, and 0. So I just grabbed a calculator because I thought for this it might be faster, but it's also cool that I could, have the computer just do this for me. And I got, when I plugged in 9 centimeters, I got 338 meters per second, 0.338 meters per second. When I plugged in 5.5 centimeters, I got 0.509 meters per second. And when I plugged in 0, I got 588 meters per second. Now here's something you should really try. Because our delta x is squared, whether this is negative or positive, we're going to get the same answer. And if you try a whole bunch of values, you're going to find out that the place where it's the fastest is actually when it's at delta x of 0. And that's because when delta x is 0, this thing goes to 0, which means all of our energy is kinetic energy. And that might bother you because up here I told you when it was 0, we had 0 potential energy. That's because I hadn't pushed on the block yet. Once I've added energy into that system, that energy isn't just going to go away. So when it's over here, we have lots of potential energy stored. When it's over here, we're no longer storing potential energy, so that's turned into kinetic. And then it'll stretch out, not drawn to scale. It'll stretch out again to 11 centimeters past here, and that would be lots of potential energy again. And you might want to try a few numbers to convince yourself, but our equilibrium point, once we've added that energy to the system, our equilibrium point will be our fastest. Now keep in mind that all I've done was a horizontal spring, so don't go applying this to other things unless you try the calculations yourself, say for a vertical spring.